Our today's topic is on energy level and electron arrangement. Welcome. Energy levels are regions found around the nucleus that are occupied by electrons. Earlier on, we learned that electrons are subatomic particles which are found outside the nucleus. So they are usually arranged in these energy levels. The arrangement of the electrons in the energy levels is called electron arrangement. The energy levels are numbered 1, 2, 3, starting with the one closest to the nucleus. Each energy level can only accommodate a given maximum number of electrons. So, we have the first energy level as the one closest to the nucleus. The next one is the second, the third, and so on and so forth. And each one of them can just accommodate a given number of electrons. Let us continue and see how many electrons are accommodated in these energy levels. Now, according to this diagram, the first energy level can accommodate a maximum of 2 electrons. The second energy level can accommodate a maximum of 8 electrons, while the third energy level can accommodate a maximum of 8 electrons. Note that the above will only apply for the first 20 elements. So it's only the first 20 elements that obey the rule of the first energy level having a maximum of 2 electrons, second energy level a maximum of 8 electrons, and the third energy level having a maximum of 8 electrons. Electron arrangement is also called electron configuration. For example, lithium, which has 3 electrons, the electron configuration is 2, then dot 1. Why? Because the first energy level can accommodate a maximum of 2. So we cannot put the 3 in the first energy level. Instead, we place 2 in the first energy level and 1, the remaining 1, in the second energy level. Boron, which has 5 electrons, the electron configuration will be 2.3. Why? Because the first energy level can only accommodate a maximum of 2. The rest of the electrons, as long as they are less than 8, they will be accommodated in the second energy level. Sodium, with an electron arrangement of 281, can be represented in a diagram like this. We can have sodium as the nucleus. Then we use crosses like this. So the first energy level will have 2 electrons, which are represented using crosses. The next energy level will have 8. 1, 2, 3, 4, 5, 6, 7, 8. Then the outermost, or the third energy level, will only have 1 electron. That is sodium. Now we go to silicon. Silicon Si with an electron arrangement of 2, 8, 4. Now here, let us use the dots. So we have silicon. The first energy level has 2 electrons in form of dots. The second energy level will accommodate 8 electrons. Then the third energy level will accommodate 4. 1, 2, 3, 4. So that is what we mean when we say electrons can also be represented in form of diagrams using either crosses or dots. Now, it can also be represented by a diagram using either a cross or a dot to represent an electron. For example, sodium with 11 electrons. They can be arranged around the nucleus in the 3 energy levels, with the first one having 2 electrons, followed by 8 electrons, then 1 in the 3rd energy level. Silicon with 14 electrons will have 2 in the innermost energy level, followed by 8 in the 2nd energy level and 4 in the 3rd energy level. Let me explain this in form of an explanation. I'm going to show this. Now, with that, you'll be required to do an assignment writing the configuration of the first 20 elements of the periodic table. We just call them the first 20 elements. Write their electron configuration. Now, having learned the electronic configuration, let's now move on to the periodic table. This is a table of elements in which they are arranged according to their atomic numbers. Now, up there is an assignment for you to write the configuration of the first 20 elements. So their atomic numbers are in order of their placement. For example, the first one, which is hydrogen, has an atomic number of 1, followed by helium with an atomic number of 2. Like that. That's how you are going to arrange them. Now, when you arrange them in that order, you come up with a table, and that is the periodic table. It is made up of periods which run across and groups which run vertically. So the periods are the ones which move horizontally. Those ones are periods. As the elements arrange themselves, the ones which move horizontally are the periods. Then we have the groups. The elements which form groups are the ones which occur vertically, which appear vertically together. Therefore, the periodic table is made up of periods and groups. It's important to know that the periods run horizontally and the groups run vertically. Now, a section of the periodic table showing the first 20 elements is as shown below. Now, let's have a look at the table below. So, we have the table of the first 20 elements of the periodic table given in form of chemical symbols. So we have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, then potassium and calcium. Those are the first 20 elements of the periodic table arranged in order. Now you can see the groups. The groups are 8, you can count, and they are normally represented using Roman numbers, Roman capital numbers. Then the periods are 4. The periods for the first 20 elements of the periodic table are 4. You can see them shown as in the diagram. Now let us note the following about the periodic table. Number 1, groups are indicated using capital Roman numbers in brackets. That is something to note. Number 2, elements with the same number of electrons in the outermost energy level are in the same group. So in the groups, it consists of elements which have the same number of electrons in the outermost energy level. Like if you look at group 1, which constitutes of hydrogen, lithium, sodium, and potassium, those are elements which have 1 electron in the outermost energy level. They appear in the same group. Same case to group 2. They have 2 electrons in the outermost energy level. They are grouped together, and so on up to group 8. Elements with the same number of occupied energy levels are in the same period. So look at the periods. We are saying we have 4 periods. Those periods constitute of elements which have the same number of energy levels. For example, if we look at period 2, which consists of lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, they have 2 occupied electrons, with lithium having a configuration of 2.1, beryllium 2.2, boron 2.3, all the way to neon with 2.8. So elements with the same number of occupied energy levels belong to the same period. Then elements whose outermost energy levels are filled up are in group 8. Look at group 8. We have helium. It has 2 electrons, the maximum number of electrons that the innermost energy level can accommodate. So because it has 2, it has its outermost energy level completely filled. So helium with neon has 828, argon has 288. So group 8 constitutes of those elements whose outermost energy levels are completely filled. Now elements in group 1 to 3 are usually metals, while from group 4 all the way to group 8 comprises of non-metals. So that is something also to note. Note also that silicon is a metalloid. It's a semi-metal. And hydrogen is a non-metal, although it is in group 1. So silicon is in group 4, and it's important for us to note that it's a semi-metal. Semi-metals are called metalloids. Hydrogen is a gas, though it is in group 1. So note that. Now between group 2 and 3, it's a group of elements called the transition elements, which have unique characteristics. So between group 2 and 3, we normally have a section which is left. If you look at our periodic table up there is a section that is left. And that is the section that constitutes the transition elements, which are unique. They have unique characteristics. For example, they have variable valencies. For example, when you talk about copper, copper does not have one valency. Copper, we have copper 1 and we have copper 2. So those are 2 valencies. That is one of the unique characteristics of the transition element. These transition elements also form colored compounds. They do not form colorless solutions, but their compounds are normally colored. They have very high melting and boiling points. Some of them form complex ions. We shall learn about complex ions in Form 4. They are good conductors of heat and electricity. For example, copper, iron, and lead. All these are metals which conduct electricity very well. So these are some of the unique characteristics of the transition element. Ion formation. Now, let us start by saying that elements in group 8 are called noble gases. Why are they called noble gases? This is because they have stable configuration, do not react with other elements, and they exist as single atoms. So they are unique in a manner. They are very stable, having stable configuration of either 2 or 8. I hope by now you know the stable configuration is having 2 in the outermost energy level or 8. They do not react with other elements and they exist as single atoms. Those are the noble gases. Atoms of other elements try to achieve the noble gas configuration by either losing or gaining electrons. So, to attain this stable configuration, all the other atoms in the other groups are trying to achieve a noble gas configuration so that they can be stable by either losing or gaining electrons. Atoms which have lost or gained electrons consequently have a charge. So they are no longer atoms, they become ions. That is why we say they have a charge. From there, we can now be able to define what an ion is. Now, a charged particle is called an ion. So these atoms which are trying to attain a stable configuration, the moment they lose or gain electrons, then they form a charged particle, which is the one we are calling an ion. Now, an ion can either be positively charged or negatively charged. A positively charged ion is called a cation, while a negatively charged ion is called an anion. When elements lose electrons, they acquire a positive charge, hence a cation. When an element gains electrons, there is an increase in the negatively charged particles, hence acquires a negative charge, the anion. Atoms with ionic configuration of 2, 2.8, 2.88 are said to be stable. Now, example, magnesium with an atomic number of 12 has a configuration of 282. It can become stable by either losing the 2 outermost electrons or by gaining 6 electrons to become a 288. But it usually loses 2 electrons. Electrons are shown using dots less energy than gaining some examples electrons. So it is easier to lose a few electrons than to gain more. In this case, magnesium loses 2 electrons. Yes, and it becomes magnesium 2 positive because 2 electrons have left. So the positive charges are more by 2. Remember, in the beginning we said that number of electrons are equal to number of protons. So if 2 electrons have been lost, then it means the protons are more by 2. So a 2 plus. Now, when drawing the structure of an atom or an ion, it is important to show the composition of the nucleus. So it is important to show how many protons are in the nucleus and how many neutrons are in the nucleus. Electrons are shown using dots and crosses. Some examples. In the first example, we have sodium with a mass number of 23 and an atomic number of 11, which means it has 11 electrons. So the 11 electrons are arranged in form of crosses as 2, 8, 1. 2 in the innermost energy level, 8 in the second energy level, and 1 in the third energy level. So what happens to sodium? It has 1 electron in the outermost energy level. So it can either lose that 1 electron or gain 7. So it requires less energy to lose 1 electron than gaining 7. Therefore, it will lose the outermost electron and have a stable configuration of 2, 8 with a positive charge. And that is how we show them in the diagram. So you put a bracket, the box bracket with the positive charge. Then you can also write it as Na, the chemical symbol for sodium, positive. That is the ion now of sodium. In the second example, we have fluorine with a mass number of 19 and an atomic number of 9, which means that fluorine has 9 electrons. So they are arranged as 2.7. Now, fluorine has 7 electrons in the outermost energy level. In order to be stable, it requires 1 electron to attain a stability of 2.8 or lose 7 electrons to acquire a stability of 2. Now it is easier or requires less energy to gain 1 electron than to lose 7. Therefore, fluorine attains a stability of 2, 8 by gaining an extra electron as shown. So the extra electron is shown as a dot to differentiate it from the other electrons which are in the form of a cross. Therefore, fluoride ion now will have 1 extra electron which will be F negative. It will have a negative charge. In the diagram, you put the box brackets again and the negative charge is shown up there as a superscript after the box bracket. That marks the end of our lesson. I hope you've learned and you've enjoyed the lesson. Let's meet in the next class. Have a good time. Thank you.